This is going to be the absolute best chapter in AP Chemistry. Acids and bases. You will see some of what you learned in your equilibrium chapter with Rice tables coming into play here. It should be pretty straightforward, although the chapter as a whole covers a lot of material and the students do find very challenging. I'm sure you'll be highly successful if you put the time in. Big Idea 6 will cover our acid and base chapter. We'll get into IMFs a little bit, but predominantly we're going to be looking at equilibrium conditions for acids and bases. From the do now, it appears that some of you remember the difference between strong acids and weak acids, and we'll delve into that in a little more detail. I do want to take some time to review some simple definitions of acids and bases. We'll be talking a lot about the Bronsted-Lowry definition. Before we do so, I want to just remind you of the Arrhenius theory. The Arrhenius theory focuses on what gets generated or produced, that is, products being made, and your solvent must be water because you must have aqueous solution. For example, a strong acid such as hydrochloric acid, you had initially said to me that strong acids ionize completely. That means that HCl doesn't stay together as a molecular unit, but rather ionizes completely into proton and chloride ion. An Arrhenius acid generates proton when dissolved in water. A strong acid ionizes completely such that the concentration of acid is equal to the concentration of proton. A weak acid such as hydrofluoric acid does not ionize completely. Equilibrium lies far to the left, and the concentration of the weak acid and the proton would not be equal. And we'll get into that more probably next time. In contrast, yep.
So with weak acids, it will always favor the acid, not proton side.
Correct. A strong base, such as sodium hydroxide, all group 1 hydroxides are strong bases, does ionize completely, and when dissolved in water, generates hydroxide ion. Again, this reaction's only going in the forward direction. This is a strong base. An Arrhenius base generating hydroxide ion. Remember, all group 1 hydroxides are strong bases. You get some from group 2 as well, CBS, calcium, barium, strontium. So calcium hydroxide ionizes completely as well, generating 2 hydroxide ion for every 1 calcium hydroxide. So with the Arrhenius definition, it must be aqueous, dissolved in water. And an acid will generate proton and a base will generate hydroxide ion. The definition we tend to focus more on is the Bronsted-Lowry definition, where an acid is a proton donor and a base is a proton acceptor. And just to review this concept a little bit before we put acids and bases together, let's say, for example, we'll have a column of acid and then looking at the conjugate base. Remember, an acid is a proton donor, so it's going to kick out a proton. A base will accept it, but the acid forms a conjugate base when the proton has been donated to another entity. For example, hydrochloric acid it will donate its proton, forming the conjugate base chloride ion. Doesn't matter strong or weak, they're both going to operate in the same regard. For example, you can have acetic acid, and when you have a Cu group, the ionizable proton is the back one off the Cu. Water can act as an acid, forming the conjugate base hydroxide ion. Let's say, for example, you had...
What are you doing?
What? Let's say you had, for example, hydrosulfuric acid. Again, you're going to donate a proton, so what will you make? HS minus, good. Let's say that you had sulfuric acid. What would the conjugate base be? Let's say you had ammonia. What would the conjugate base be? Let's say you had a hydronium ion. What would the base be?
Water.
Let's say you had an ammonium ion. What would the base be?
Ammonia.
Let's say you had hydrogen sulfate ion acting as an acid. What would the base be? Sulfate ion. You got it. All right, so acids are proton donors, and they form conjugate bases. On the flip side of that, bases are going to be proton acceptors, so we're going to pump a proton in to generate a conjugate acid. For example, chloride ion would form what conjugate acid? Sulfate ion would form what conjugate acid? Hydrogen sulfate ion. Pick a base.
Bicarbonate ion.
What would that form?
Carbonic acid.
And this could act as an acid or a base, right? Because some species are what we refer to as amphiprotic or amphoteric, and they have the ability to act as an acid or a base. You'd see that with bicarbonate ion, you'd see it with hydrogen sulfate ion, you'll see it with water and ammonia. When water acts as a base, it accepts a proton, forming the hydronium ion. What would ammonia form?
Ammonia.
All right, so this you're remembering from baby chemistry last year, correct? Go ahead, Sam. Q.
What? You know how like there's ammonium for NH4 and ammonia for NH3? What is NH2? Like, is there like a name?
NH2 1 minus is an amine. It's an amine ion, if you will. Generally speaking, amines are bases like methylamine and things
And
like
how
that.
do you differ between if the NH3 is the base or the acid?
It depends on what it's reacting with. If you know what's generated, you might be able to predict it. If you don't know what it's generating, there may be more than one answer, and we'll take a look.
If you had both NH3 and H2O in the problem,
Okay, so let's say you had this.
and you just didn't know what was being generated.
Okay, so if you did not know what was being generated, in this case, there's more than one answer. Let's say that this is the acid and this is the base. This is the proton donor forming hydroxide ion, the conjugate base of this acid, and then the conjugate acid of that base would be as such.
Or you could do it the other way, where the other one is the acid.
Exactly. Or the other possibility would be that you generate hydronium ion and this anion here, and then this would be the conjugate acid, and this would be the conjugate base, and in this case this would be a base and an acid. So in some instances you don't know. But if, for example, you had, let's say, perchloric acid and ammonia. This species must be an acid. It doesn't have the ability to gain another proton, and we'll talk about why in just a minute. So this is perchlorate ion, and this is the conjugate base. Here's my base that's accepting the proton, generating the conjugate acid. And in regard to knowing that this is an acid and it can't be a base, that's actually not correct for Bronsted-Lowry, because Bronsted-Lowry bases do not have to contain hydroxide ion. We looked at all of these and none of them do. Certain substances don't have diprotic capabilities, but it's probably easier to remember in this regard with two exceptions. For example, if you had a sulfide ion, if that were acting as a base, it would generate hydrogen sulfide ion. Typically, the most H's you can gain or accept is based on your charge. So for chloride ion, you can get to hydrochloric acid, but you could not do that. It doesn't exist. This typically works, for example, with perchlorate ion. It can act as a base and form perchloric. Perchloric acid. The two exceptions I can think of, with oxide ion, you know you can make water, but you also know you can make hydronium ions. So there's an exception right there. And the other one is, you know you can make ammonia, but you can also make ammonium ion. And those are the only two exceptions I can really think of. I don't think there are any others, although not sure. The other thing I do want to mention, because this was a little bit messy on the semester exam, remember if you're drawing these, you have 5 valence electrons, you have 4 times 1, and then you subtract 1 for the 1 plus charge is a total of 8. And when you draw this, be careful. A lot of you made a big mess, and we're not going to make the same mistakes twice. And you've got 2, 4, 6, 8. All right, and those are all single bonds, of course, to hydrogen. Anyway, you react Bronsted-Lowry acids with Bronsted-Lowry bases and generate conjugates.
So you know how when you react a strong acid with a strong base, you get salt and water? It's the same thing occur.
When you react a strong Arrhenius acid, or actually, when you react an Arrhenius acid with an Arrhenius base, you get a salt and water. So if you have an Arrhenius acid and an Arrhenius base, you generate a salt and water. When you have Bronsted-Lowry acids and bases, such as this, you generate conjugate acids and bases. Be careful.
But if you have like a weak Arrhenius acid and a weak Arrhenius base, does it still generate salt and water?
Yes.
Like if you had sodium bicarbonate and
Sodium bicarbonate is a
acetic
salt.
acid.
Hang on. If you had
they're
acetic,
also weak base.
it has some basic entity in terms of pH, but it'd be classified as a salt. If you had acetic acid and, let's say, magnesium hydroxide, a weak base, that would generate magnesium acetate, a salt, and water.
How do you tell the difference between like an Arrhenius reaction versus a Bronsted-Lowry reaction?
An Arrhenius base has hydroxide ion in it, and a Bronsted-Lowry base doesn't.
But
Have
can
to.
a Bronsted-Lowry base, Bronsted-Lowry, you know what I mean, have hydroxide in it?
I think once it has hydroxide ion, it would be classified as Arrhenius.
Okay.
How do you tell if it's a Arrhenius acid?
Yeah, that'd be very tricky. You could only just tell if it was dissolved in water or not. And you're not gonna have to make the distinction.
Okay.
Is that reaction reversible? You go from salt and water to an acid and base.
I'm gonna say no, because if you react this salt with water, you're just gonna, if it's water soluble, you'll just dissolve it into magnesium ion and acetate ion. All right, so when you react an acid with a base, you get their conjugates, as we mentioned. Here's hydrochloric acid and water acting as a base, generating the conjugates. And we can take a look at this. And I'm sorry, the sound system is atrocious.
The Bronsted-Lowry concept defines acids as proton donors and bases as proton acceptors.
Morse
In
code.
the reaction of aqueous hydronium ions and ammonia molecules, the hydronium ion acts as the Bronsted-Lowry acid, and the ammonia molecule as the Bronsted-Lowry base. The net effect is that of a proton transfer from hydronium to ammonia, forming water and the ammonium ion.
We
We did it.
Why does it do that?
I don't know, Samuel.
No, but I wasn't
The
paying
D
attention. I
that
think
is-
it should sound like
So again, an acid and water, and typically, they'll go ha-ha. Generating proton. Here's your conjugate, here's the other conjugate. And what you can see here is your acid. It's going to donate its proton to the base. The base forms the conjugate acid, and the acid forms the conjugate base. And we'll get into that in just a sec. It looks bad, but it's not, I promise. It's easy. Some of you did a little bit of it last year. If you had Mrs. Vera, she did do KAs and KBs, so you're a little bit ahead of the game, which is good.
Or if you
first time.
really, because I said AP chemistry for this, so.
Alrighty. Great.
You just can't go into anything with the expectation that Chase will know less.
Can we please be nice to one another?
I am being nice. I'm saying Chase.
Can we
Enjoy
please be
supportive
nice
friend.
to one another? As I mentioned, amphiprotic or amphoteric, these have the ability to act as acids or bases. They can gain or lose. Let's take a look here. First example, look at your reactants. What's the acid? What's the base? Here's the acid. It donates the proton to the base. So base, acid, conjugate, base. And so here, this is what you had asked me earlier, Sam. I'm looking at both species in red here. I can see the acceptance of the proton, hence the base and its conjugate acid, even though both of these species are amphiteric, and they have the ability to act as either. But if they give you products, you can figure out which is which. Looking at this example shown here, what's the acid? Definitely phosphoric acid. It donates the proton to the water as such.
Is amphiprotic and amphoteric the same thing?
Yeah. In this example shown here, I want to point something out as well because this came up one year. I can do it for either one. Let's take phosphoric acid reacting with water to generate dihydrogen phosphate ion and hydronium ion. And we established that this is the acid, this is the base, this is the conjugate base, and the conjugate acid. One year on an AP exam, they asked for a conjugate acid-base pair. That doesn't mean that they're both the conjugates. It means you have an acid with its conjugate base, or a base with its conjugate acid. So if they ask you for a conjugate acid-base pair, you need those complementary pieces, if you will. For example, phosphoric acid with dihydrogen phosphate ion, or you could have picked water with hydronium ion. So be very comfortable selecting a pair.
When we had to memorize all the polyatomic ions, a lot of the hydrogen-containing ones weren't on there. Can you add that to any ions? Like, can you add dihydrogen sulfate ion?
No.
Or just hydrogen sulfate ion?
Yes, but it's not, if it has the ability to have more than one. So for example, this is sulfate ion, and this is hydrogen sulfate ion.
Each one takes away one charge, right?
Uh-huh.
Yeah.
Sulfite ion, hydrogen sulfite ion.
That's why you can have dihydrogen phosphate, because it's 3 minus.
Hang on. Carbonate ion. This is hydrogen carbonate ion or bicarbonate ion. What did you say?
Is that why you can have dihydrogen phosphate as well as hydrogen phosphate?
Right. So phosphate ion, but then you can have 2 different kinds of phosphate ions with hydrogen species attached, and that's where you do specify monohydrogen phosphate ion and dihydrogen phosphate ion. But you don't see that for everything, like with an arsenate. I don't.
Or like a chlorate. Well, you can't have it with a chlorate.
No, because it has 1 minus, so it has to have at least 2 minus. But these are the, I think these are the only ones that exist. But I hate to
So
say
that
that.
wouldn't be like a hydrogen chromate.
I don't know. I don't think. No, I take that back. Yeah, you could have like a hydrogen oxalate ion, but we're really getting nitpicky. Alrighty. The same way we wrote KEQ expressions, we can write KA expressions. For example, if you have an acid and you are reacting it with water, therefore aqueous, you generate acetate ion and hydronium ion, and the Ka is equal to the product concentrations over the reactant. What happened to the water? I forgot to put it in. It's a liquid, so we're not going to include liquids. This Ka value is 1.8 times 10 to the negative 5, relatively small, because acetic acid is a weak acid. Ka is less than 1 are indicative of a reverse direction being favored, weak acid. Go ahead.
How do you know it's 1.8 times 10?
That would be given.
That'd be good.
How do you know, what's the difference between that and KP? Not KP, KC.
Right, so that was exactly what I was going to say. Good question. With KEQ, in the previous chapter, we talked about KC, KP, and we also mentioned Q, but Q is not at equilibrium. That's non-equilibrium conditions. In this chapter, we have Ka, and that's when you have acid ionization constant, so you're going to have an acid reacting with water, or just dissolved in water. Kb for a base, and we'll get into Kw next time for water.
Are those all at equilibrium?
What about like PK and PKC?
You can have a pKa and a pKb and a pKw, and you should remember pH, and we'll talk about those next time.
And POH.
One big happy family.
And POH.
All right? You can have a base ionization constant, Kb. For example, ammonia can act as a base, generating ammonium ion, and hydroxide ion, again, products on top, reactant on the bottom. It's a coincidence that the Ka, Kb values are identical here. Let's do this first one together. You'll try the second one. Incidentally, amines are typically bases. In the first problem, it says write the acid or base ionization constant of propanoic acid. Here's propanoic acid. your best approach here is you want to know the Ka expression. In order to get the Ka expression, you can react it with water, liquid, and you will generate a propanoate ion and hydronium ion. We include ions because they are aqueous. And we put it over the acid. And that's my Ka expression. And this is particularly useful because if you know the Ka and you know the concentration of your acid, you can calculate the hydronium ion concentration and the pH. This is a weak acid that doesn't ionize completely, so these two concentrations are not the same. This is far greater than that.
Do you have to have a number for propanoic acid because the carboxyl group is such a high
No.
functional group?
No. What do you mean a number?
Like, do you not have to say, like, one propanoic acid?
No,
per acid?
because you're misunderstanding the naming system there. No. I'll answer that separately. It's just going to be confusing. Sam?
So it's a weak acid, so the concentration of the acid and the base aren't the same. But the concentration of the acid and like the acid and the conjugate acid.
No. This concentration will far exceed either of these, and we'll take a look at why in a few minutes.
Okay.
All right. The second one says, write the acid or base ionization constant of methylamine, and they give you methylamine. See if you can do this one. And it's on the screen. Go ahead. See if you can do it. And a hint is that it's a base. Did you get what I got? Yes, yes? That's how your mini quiz is going to open up. We won't worry about it this week.
I'm gonna need one.
Remember, bases generate hydroxide ion. And again, you'll see the concentration of this will far exceed the concentrations of those because it's a weak base. Another thing that you will see is that the weaker the base, the stronger its conjugate acid. The weaker the acid, the stronger its conjugate base. And when you're predicting the direction in which equilibrium, if you're predicting the direction the reaction will proceed on in the equilibrium reaction, you look for the strongest entity. For example, an acid-base reaction is favored in the direction from the stronger member to the weaker member of each conjugate acid-base pair. For example, here you have acetic acid and bromide ion reacting to form hydrobromic acid and acetate ion. You know that hydrobromic acid is a strong acid. That's the strongest member, and therefore the reverse reaction is favored because it always goes from strongest entity and then down toward its weaker counterpart. If you're considering the relative strengths of some bronzed-Lary acids and their conjugate bases, hydroiodic acid is the strongest, then hydrobromic, then hydrochloric. And these are 3 binary acids. And we'll explain why hydriodic acid is stronger than the other members of group 17. Sulfuric acid is strong as well. Nitric, there are some other strong acids too. So increasing strength of the acid as you go up. The stronger its acid, the weaker its conjugate base, so the increasing base strength as you go down.
Does it have to do with the activity series of the halogens?
No. It differs for binary versus ternary. For the binary acid shown there, when you consider hydriodic being the strongest, iodine has the largest radius compared to bromine and chlorine. And let's say that, H is like a skinny little child, and you can think of pregnancy. So here's 3 months, here's 6 months, and here's 9 months. And it's hard to get your hands around the waist of somebody who's 9 months pregnant. And so those two cannot get as close together, the H and the I. So it's easier to break the bond, hence the stronger the acid, because the stronger the acid, the more readily and quickly it ionizes. And so that's based on radius. But with ternary acids down a group, it's not based on radius, it's based on electronegativity, and we'll talk about that. Also with binary across a period, it's based on electronegativity, so it's tricky. We've mentioned the strong acids previously, and this is what I wanted to show you in regard to concentration. Here's your strong acid HA, and when you compare this particulate diagram with this, what do you notice? 100% dissociation or ionization. And so the concentration of the acid is equal to the concentration of the proton and the anion if it's monoprotic. For a weak base, and they use HB as an abbreviation, which is a disaster area, but this is a weak acid. Did I say weak base? Yeah, and that's because HB to me was always based on basic properties. So HB here they're calling weak acid. Comparing these two particulate diagrams, what do you notice? Not very dissociated, very little dissociation, and you can see here that concentration has dipped slightly for the weak acid, but the concentration of proton and anion here is very, very low compared to the weak acid, so you don't get that equal amounts that we mentioned previously. So if you're considering strong versus weak, that's actually kind of blurry. You're going to see it better here. No difference? Oh.
Yeah.
The Ka value for a strong acid is large, going to typically be greater than 1. Weak acid is small, times 10 to the negative exponent. Percent dissociation, far to the right for strong, far to the left for weak. Concentration of proton and acid is going to be the same for strong. The proton concentration will be considerably less for weak, and we'll learn how to calculate that later in the week. Strengths of conjugates, strong acids have weak conjugate bases, weak acids have stronger conjugate bases. So those are some key comparisons between the two. The other thing I want to mention briefly in regard to binary acids, and we alluded to this already, you know how to write and name acids, hydrofluoric, hydrochloric, hydrobromic, hydroiodic for group 17. From group 16, you're going to have 2 protons. So you've got water, hydrosulfuric acid, hydroselenic acid, hydrotelluric acid. Group 15, you're going to have 3 protons. So you've got hydronitric and hydrophosphoric. Remember, it's always hydro and ic.
Is hydronitric acid common?
No. Down a group, the strengths of the acids are going to increase, and this is based on the radius. In order for this entity to dissociate, the HF bond or the HCl or HBr or HI bond has to be broken. The more readily that bond is broken, the stronger the acid. And what you find is the larger the radius, the weaker the bond, the lower the bond energy, and as a result, the stronger the acid. And that is based on radius as we described.
So hydrogen or iodic acid is, or did I say that right?
Hydroiodic acid.
Is the strongest acid.
Of the four that you're looking at, hydrofluoric, hydrochloric, hydrobromic, and hydroiodic. Hydrofluoric is actually weak. The H and F are so tightly packed together that it doesn't readily ionize. Across a period, though, and this is where it gets confusing because it's only down a group binary that the radius is the key. Across a period, you'll see acid strength increases as well, but this is based on electronegativity. As the electronegativity increases, the bond dissociation energy decreases, the acid strength increases. This is a little trickier. For example, if you had hydrofluoric acid, you know fluorine is the most electronegative element. You're going to see a partial negative here, a partial positive here. That weakens this bond, making it easier to clip than if, for example, you had a water molecule where, again, you'd have dipoles, but this bond strength here, if you will, is a little bit stronger than this, and this is a weaker acid than hydrofluoric acid. And if you want to learn more about hydrofluoric acid, they had a great segment on it in Breaking Bad, like season 1, where he told them what kind of container to get. Oh, yeah. We'll take a look at that.
You watch Breaking Bad, Dr.
No.
I thought Kevin still watched that.
I haven't seen it all yet. Don't ruin it for me.
I've never seen it.
I don't watch it either.
All right. In regard to your oxy acids or your ternary acids, this is going to have an HO and then some other element here. Be careful. The H must attach to an O. They often ask you to draw these. We'll draw one out, and it's a disaster area. If element E has a high electronegativity, the OH bond weakens and the acid will be stronger. So if you compare increasing acid strengths of hypoiodous, hypobromous, and hypochlorous acid, you will find that this acid is of greater strength than those two because chlorine is more electronegative than the others, which weakens the bond. For example, if you were looking here, versus here, chlorine is more electronegative, and that results in a weakening of this bond, more easily severed. This, guys, cut it out. This is a stronger acid than this. So for ternary acids, it's based on electronegativity as well. Be careful there. The other thing that you find is if you compare acid strength of hypoiodous, now hypochlorous, to, let's say, chloric acid, the more oxygen atoms you have, the greater the electronegativity, the more this bond is weakened, and we know chloric acid is a stronger acid than hypochlorous acid. So those are all comparisons you want to make. Be sure to attach the H to an O. A lot of kids will put H on Cl and you haven't drawn an acid, you've drawn nothing. Be very, very careful there. That is important. Don't muff the drawing. So just to review, in regard to acid strength, for binary acids, in terms of down a group, that's based on the radius. For binary acids across a period, that's based on electronegativity. For ternary acids, your basis is electronegativity. Be careful there. The more electronegative an element attached to the O, or the more O's you have, the greater strength of the acid. We're going to get into acids and bases a lot more. We're going to talk about self-ionization of water next week. At this point, you just want an understanding of how to write Ka and Kb expressions. We'll get into solving them later in the week. And in this particular chapter, we have a very cool lab on acid-base titration, where we're generating titration curves and then analyzing them. Questions? All right, and we'll pick up with acids and bases later in the week. You want to really stay on top of this chapter. It's 2 chapters in one. They're very long and they can be very tricky.